Here is a numerical type question. Work through the numbers carefully. Let us solve it step by step. Let us begin solving this step by step. Identify the starting material. The structure shown is a cyclopentane ring bearing an exocyclic double bond with a methyl group. Specifically, it appears to be 1-methylcyclopentylidene or a cyclopentane with a methylated exocyclic alkene consistent with 1-propan-2-ylidene, cyclopentane or 1-methyl-1-vinylcyclopentane type structure. Looking carefully, it is a cyclopentane ring with an exocyclic double bond bearing a methyl group, i.e., cyclopentylidene with methyl is equal to methylene-cyclopentane with methyl substituent on the double bond carbon. Moving on to the next step. Ozonolysis, O3 then ZnH2O reductive workup, cleaves the C is equal to C double bond to give two carbonyl fragments. Since the double bond is exocyclic to the cyclopentane ring, ozonolysis opens it to give a diactone ketaldehyde. The cyclopentane ring carbon bearing the double bond becomes a ketone, cyclopentanone carbonyl, and the exocyclic is equal to C, CH3, becomes a methyl ketone, acetaldehyde or acetone depending on substitution. The product Y is a decarbonyl compound, specifically a ring-opened or tethered diactone. Given the exocyclic methylated double bond on cyclopentane, ozonolysis gives a 1,6-diactone or similar, cyclopentanone with a pendant CH to CH2 or C is equal to O, CH3 group. More precisely, Y is 2,2-oxopropyl, cyclopentanone or a related diactone with the two carbonyl groups positioned for intramolecular aldol. Moving on to the next step. The starting alkene is 1-prop-1-N-2-Yl, cyclopentane, isopropenyl cyclopentane, cyclopentane ring with C is equal to C, CH3, exocyclic. Ozonolysis of this trisubstituted disubstituted exocyclic alkene, one fragment is cyclopentanone from the ring carbon, the other is acetone from is equal to C, CH3, 2 if disubstituted, or acetaldehyde if monosubstituted on that carbon. Actually, the image shows a methyl on the exocyclic double bond carbon, making it is equal to CH-CH3 or is equal to C, CH3. If the alkene is cyclopentylidene CH-CH3, i.e., one substituent methyl, reductive ozonolysis gives cyclopentanone plus acetaldehyde connected. But since the double bond is within the molecule, Y must be a single decarbonyl compound, 2-oxothyl, cyclopentanone or similar. And for the final step, Y is equal to a decarbonyl compound capable of intramolecular aldol. The exact structure of Y from ozonolysis of the shown alkene, cyclopentane ring with IChO methyl substituted alkene, is to acetylcyclopentanone type or a ketaldehyde. Given that the answer is 3, Y must have multiple acidic alpha hydrogens at different positions, allowing aldol condensation via different enolizable positions attacking different carbonyl groups. For an intramolecular aldol condensation, the enolate of one carbonyl attacks another carbonyl within the same molecule, followed by dehydration, heat. Y is a 1,6 or 1,7 decarbonyl compound. Different alpha positions can be deprotonated, and each enolate can attack either carbonyl carbon, giving different ring sizes and structural isomers. Considering all possible combinations of which alpha carbon forms enolate, X, which carbonyl is attacked, and accounting for distinct structural products, including stereoisomers counted as one, but constitutional isomers and different ring size products counted separately, 3 distinct intramolecular aldol condensation products result. 1. Enolization alpha to one ketone attacking the other carbonyl forming one ring size. 2. Enolization at a different alpha position attacking the same or other carbonyl forming a different ring size. And 3. A third combination. All three represent distinct constitutional isomers of cyclic enone products. Therefore, the correct answer is 3. Therefore, the correct answer is 3.